This video is on what a coefficient does to a parent graph that you know. For example, or not for example, but in other words, in symbols, if you know the graph of y equals f of x and you put a number times f of x, what does that do to the graph? But before we get to that, we have to do page 0 here, and it's what this means. What happens when you put a negative sign in front of an expression like this? What does it mean? Well, it means you square the number first and then make it negative. It does not mean you make the number x negative and then square that and get a positive. Okay? A negative sign is exactly like multiplying by negative 1. So negative 3 squared is the same as negative 1 times the quantity 3 squared, so it equals negative 9, not 9. So a negative sign comes after the exponent in PEMDAS because the negative sign is the same as multiplying by negative 1. Okay, so we'll break this into two parts. The first is, what is the negative, if a coefficient is negative, what does that negative do? And the second is, what does the numerical value of the coefficient do? All right, so look at these two examples. Here's your parent graph, y equals x squared, all very familiar. And here's y equals negative x squared. So the coefficient, the a, is negative 1. So this means you square x, and then you apply negative. So all those values that were positive over here become negative for all the corresponding same x values. So for every x value, instead of going up to the positive value of y, you go down to the negative value of y. In other words, it just flips the graph across the x-axis when you put a negative in front of the parent function. Here's another example with an odd function instead of an even function. Here's the familiar y equals x cubed graph. And then here, every single one of the y values has been negated, so it's the opposite. So here in green dotted lines is y equals x cubed. That's from over here. And then in purple is the graph from this, y equals negative x cubed, where every value, for any value of x, what would have been up here has been made negative, and would have been down here has been negative of a negative, so made positive. So it flips the graph across the x-axis. So here's the conclusion for a negative coefficient. Graph negative of a function. You sketch the function lightly in pencil. That should be a parent function that you know. Then you reflect it across the x-axis. In other words, pretend there's a mirror on the x-axis. And for every point that's in the original graph, lightly sketched in pencil, you find its mirror image point as if the x-axis is a mirror. In other words, for the same value of x, the y becomes its opposite sign. So here's an example you could get on a standardized test where you're not giving any specific function or numbers, you're just given a graph, a curve, and you're asked to graph the negative. So what you do is for every point along here, you take the exact same value of x, but you go across the x-axis and plot the negative of that for y. It's easiest to start with where it's 0, because the negative of 0 is 0, so these two graphs will intersect when y equals 0, and then go from there. Alright, so that's what you would get if you reflected the green one across the x-axis and got the pink one. For any x value, the value in the green one, you find the corresponding mirror image point down here where the y has its opposite sign. So when the original y is negative, the new y is positive, etc. Okay, the second half is to discuss how the numerical value of this coefficient affects the graph. And we'll do three examples. That numerical value is either going to be 1, which just gives you your parent graph, larger than 1, or less than 1 in absolute value. We're going to ignore the sign because we just learned how to deal with the sign. So you deal with those two things separately. First, you look if it's positive or negative, and if it's negative, you reflect the parent graph across the x-axis. Then you look at its absolute value. If the absolute value is bigger than 1, you do one thing, and if the absolute value is smaller than 1, you do something else. So you can see what the absolute value bigger than 1 does. It makes every single y value bigger by the same factor. And if it's smaller than 1, it reduces every single y value. These are points, not negatives. So that's 0.1, 0.1. It makes every y value smaller by that factor. In other words, you're dividing every y value by 10. So you should compare this graph with the original and this graph with the original. Okay, here are these values graphed. Here's our original function, y equals x squared. Here's when the coefficient in front is larger than 1. That will be the purple graph. So still in green is y equals x squared, the original graph. And every single value of y has been multiplied by 10. Now this isn't very well to scale. Of course, that's not really 10 times bigger, but it's not too bad. So every single value of y has been increased by 10. Notice it doesn't stay under for a while and then curve up through the 0.11 and then go above it the way it would if this were y equals x to the fourth. So this is different from making the exponent bigger. What we're doing is making the multiplier coefficient in front bigger. So that lifts every y value up higher than it would have been otherwise. It creates what looks like a narrowing, but it's more of a multiplication, a stretching upward. And if the coefficient in front is smaller than 1, then it's really like dividing by a number bigger than 1. So that creates this silver graph here, which is always under the green graph. Every value of y is 10 times smaller than the original value of y for the same value of x. So here's the conclusion. If you multiply by a coefficient, two cases to think about. Is the coefficient bigger than 1 or smaller than 1 in absolute value? So if the coefficient is bigger than 1, then it stretches the graph vertically. Each y value is larger in absolute value than for y equals f of x, the original graph. And if a is smaller than 1, we call that a shrink, not a stretch. Also, it shrinks the graph vertically. Each y value is smaller in absolute value than it would have been for the original graph. We're ignoring the positive or negative sign because we dealt with that in the first part of the video. Okay, so here's the kind of problem you could get on a standardized test. The original function, the parent function, is y equals f of x. That's shown in green. And in purple, we're going to sketch what happens if you multiply that by 2. In other words, the coefficient up front is larger than 1. Again, the best place to start is when the function is 0, when y equals 0, because they're going to be equal at that point. And now for every point, we should pick something that's twice as high. So like right here, we go twice as high. Right here, twice as high will be kind of off the graph. Here, twice as high. Here, twice as high. And so it looks like that. It gets stretched up higher, twice as high, goes a little bit off the page, and comes back down, always twice as high. So there, twice as high, like that. Goes like that, and always stays above the green, twice as high above the green. And here, when the function is negative, when the y value is negative, the purple y value will be larger in absolute value, which means it'll be more negative. So instead of like maybe here it might be -1, it'll be -2. Here instead of maybe -2, it'll be -4. So here it's under, but the way to think of that is bigger. Y is bigger but negative. When we're multiplying by a coefficient less than 1, multiplying by 1/2 is like dividing by 2, so everything is half as big. So you go here and go half as big. Here, half as big. Here, half as big. Again, goes through 0 again, like that. Y equals 0 up there, half as big. And right here, also half as big. I did that wrong, not that, but this. Half as big, like that. All right, so that's what happens when you multiply by a coefficient larger than 1. Stretches it farther away from the x-axis. Smaller than 1, compresses it or shrinks it down closer to the x-axis everywhere, but wherever y equals 0, it will be 0 no matter what.